The Taklamakan Desert, China's largest desert. For decades, its sands crept outward.
The government of China, trying to find a solution to this problem, embarked on the journey of transforming its desert into green forests.
Before sunrise, the Taklamakan lies in a muted haze, its dunes rising like frozen waves around a desert long believed incapable of sustaining anything but silence. Yet, beneath this stillness, a transformation was already unfolding, one that would reshape both the surface and the depths below, revealing how a hostile wilderness became an engineered refuge for carbon and life. The desert that defined silence. For centuries, the Taklamakan Desert existed as an expanse so vast and unforgiving that travelers described it as a boundary between worlds, rather than a place within one. Its dunes, shaped by relentless winds, shifted with a quiet persistence that erased roads, engulfed villages, and pushed migrating sandfields closer to the oases, sustaining life along the Tarim River. Scientists who studied the region viewed it as a biological void, with almost no capacity for ecological resilience. Yet, they also recognized signs of an elusive process occurring beyond human perception. While communities on the desert's margins fought encroachment through makeshift barriers and seasonal labor, researchers began to question why atmospheric carbon measurements across western China occasionally showed unexplained deficits. These anomalies hinted that the desert's silence masked more than emptiness, suggesting the presence of a hidden mechanism influencing global carbon cycles in ways no model could fully explain at the time. As the 21st century progressed, the urgency surrounding desertification intensified, drawing policymakers, hydrologists, and ecologists into a growing conversation about the interplay between climate instability and expanding arid zones. Their investigations revealed that the Taklamakan was not merely advancing across the landscape, but interacting with it through dynamics far more complex than surface observations suggested. This realization created the foundation for a scientific inquiry that would eventually uncover how the desert itself was participating in planetary carbon regulation. The hidden ocean and the vanishing carbon. When researchers shifted their focus beneath the dunes, they uncovered a subsurface world far larger and more active than anyone had imagined. The Tarim Basin contains one of the planet's most extensive hypersaline aquifers, a vast body of mineral-rich water that circulates through deep geological structures while absorbing atmospheric carbon carried downward by meltwater from the surrounding mountain ranges. As this water descends, it behaves much like a pressurized carbonated solution, dissolving carbon dioxide with remarkable efficiency and transporting it into isolated chambers thousands of meters below the surface. These saline reservoirs, locked away from biological processes, provide ideal conditions for chemical reactions that gradually transform dissolved carbon into stable carbonate minerals. Over millennia, this mechanism created a hidden archive of carbon, yet scientists had not realized how dynamic the system truly was. Recent geochemical studies revealed that mineralization in these aquifers can occur far faster than earlier estimates suggested, with certain zones able to convert dissolved carbon into solid carbonate within only a few years. This accelerated transformation challenges long-standing assumptions about natural sequestration rates, demonstrating the deserts like the Taklamakan possess the capacity to lock away carbon on timescales relevant to contemporary climate strategies. The discovery reframed the basin not as an inert geological formation, but as an active carbon engine operating in silence beneath one of Earth's harshest environments. As these findings gained international attention, they inspired new lines of inquiry regarding the relationship between surface conditions and underground sequestration. Scientists began to explore how moisture pulses, groundwater flow patterns, and seasonal temperature gradients influence the depth and speed of carbon migration through the basin. Their work illuminated a subterranean system thriving in the absence of life, yet profoundly intertwined with the evolving climate above, creating a natural prelude to the human interventions that would soon reshape the desert's outer rim. Engineering a forest against the sand. Long before the full complexity of the Taklamakan's subterranean carbon vault became understood, China had already embarked on an ambitious experiment along the desert's shifting perimeter. In 1978, planners launched the 3 North Shelter Belt program, an undertaking meant to slow desertification through the creation of a continuous ecological barrier stretching across vast northern regions. What began as a defensive measure evolved over decades into one of the most extensive environmental engineering projects in human history, culminating in 2024 when the final gap in a 3,046 kilometer vegetative ring around the Taklamakan was finally closed. This achievement represented not only a symbolic milestone, but also the consolidation of a landscape-scale intervention that fundamentally altered the desert's relationship with surrounding ecosystems. Crafting a forest in a region defined by drought and salinity required careful experimentation with species capable of surviving conditions lethal to most plants. Foresters selected hardy candidates such as Populus euphratica, a desert poplar tolerant of high salt concentrations, and Tamaris, a shrub with deep rooting systems able to tap scarce groundwater. Over time, these species established a resilient front line capable of anchoring dunes, reducing wind erosion, and creating microhabitats in areas once devoid of biological function. Satellites equipped with solar-induced fluorescence instruments later detected measurable decreases in atmospheric carbon concentrations along the desert's rim, offering visual confirmation that this engineered forest was actively drawing carbon into its growing biomass. The Green Ring's expansion transformed the region into a dynamic ecological corridor where sand, vegetation, and climate began interacting in previously unseen ways. What had once been regarded as an immutable wasteland gradually evolved into a managed system capable of supporting life while buffering nearby communities from the advancing desert. This shift laid the foundation for the next phase of the project, during which technology and human participation would amplify the forest's reach beyond traditional ecological limits. The gamification of ecology. As the Green Ring expanded, its maintenance demanded levels of precision and endurance far beyond what seasonal labor crews could reliably provide. The planting window in the Taklamakan remained extraordinarily narrow, with only a brief period each spring when soil temperatures, moisture levels, and wind conditions aligned well enough for saplings to survive. To meet these constraints, engineers introduced autonomous reforestation robots equipped with LiDAR sensors, onboard irrigation systems, and machine learning models capable of identifying optimal microsites between unstable dunes. These robotic clusters moved methodically across the landscape, planting thousands of seedlings per day while adjusting their techniques in response to shifting terrain and real-time moisture readings. Their consistent accuracy significantly increased sapling survival rates, enabling the forest to expand at a pace unattainable through human labor alone. Alongside these technological efforts, public participation emerged through an unexpected avenue, a mobile platform that transformed environmental stewardship into a daily digital habit. The Ant Forest app encouraged users to accumulate virtual green energy through low-carbon behaviors such as walking, cycling, or choosing public transit. Once enough energy was collected, the app triggered the planting of a real tree in the desert, linking personal choices in urban environments to tangible ecological outcomes hundreds of kilometers away. This system fostered a sense of shared ownership and collective momentum, demonstrating how behavioral incentives could magnify the impact of large-scale ecological engineering. Together, the synergy between automation and citizen engagement revealed an evolving model of environmental restoration, one where technology, policy, and personal action converge to sustain a vast living infrastructure at the desert's edge, the albedo paradox, and the water dilemma. As the forest matured along the Taklamakan's perimeter, researchers began examining how this sweeping transformation altered the region's energy balance and hydrological behavior. Desert sand naturally reflects a significant portion of incoming sunlight, creating a high albedo surface that limits heat absorption. Dense vegetation, however, absorbs far more solar radiation, prompting questions about whether large-scale greening might unintentionally warm the surrounding air. Initial models suggested that increased evapotranspiration from millions of trees could counteract this effect by releasing moisture that cooled the atmosphere. Yet, scientists recognized that this delicate balance depended heavily on the long-term availability of water. Without consistent groundwater recharge, The very trees responsible for cooling could weaken, darken, and eventually die, leaving behind heat-absorbing biomass capable of intensifying regional temperatures. The water sustaining these plantations originates primarily from glacier-fed rivers descending from the Kunlun and Tian Shan mountains, making the system vulnerable to shifts in seasonal melt patterns. Climate projections indicate that accelerated glacial retreat could reduce stream flow in future decades, raising concerns about whether the Green Ring might outgrow the hydrological capacity that supports it. Ecologists warn that widespread vegetation stress could shift the ring from a carbon sink to a potential carbon source, especially if large numbers of trees decline simultaneously. These risks complicate the narrative of success, revealing that even ambitious ecological engineering operates within constraints shaped by climate variability and resource competition. This tension between benefit and vulnerability encouraged policymakers to reassess long-term management strategies, guiding the transition toward a broader geopolitical understanding of how environmental restoration intersects with regional stability. Geopolitics of a manufactured climate frontier. As China refined its approach to desert stabilization, the Green Ring began influencing diplomacy in ways few had anticipated. The nation's rapid transition from industrial emitter to environmental innovator reshaped global perceptions, positioning its desert reclamation strategies as exportable tools for regions confronting advancing sands. Countries participating in the African Great Green Wall and several Middle Eastern states adopted variations of China's sand fixation methods, creating partnerships that blended ecological restoration with infrastructural and technological assistance. These collaborations strengthened China's soft power while expanding its role in shaping global climate adaptation policies. Yet, the project also intensified debates over resource allocation, particularly regarding the glacier-fed waterways sustaining both the forest and downstream agricultural zones. Neighboring regions questioned how long-term water use might shift under continued expansion, prompting discussions about transboundary hydrological rights and ecological responsibility. The Taklamakan's transformation, once viewed as an isolated national undertaking, evolved into a case study demonstrating how environmental engineering can influence political relationships and strategic planning. This geopolitical dimension reframed the desert not simply as a restored landscape, but as a frontier where climate action, regional diplomacy, and national ambition converge with consequences extending far beyond its encircling forest. Across the Taklamakan's shifting rim, a desert once defined by silence now reflects humanity's capacity to reshape its future, blending hidden geology with deliberate design. Let this story inspire deeper curiosity, continued learning, and a commitment to supporting projects that protect fragile landscapes and strengthen our shared planet.